Okay, it has started. I am going to be doing the live coding of a little graphical design that I produced in processing. Processing is a Java environment, which allows you to do different things fairly easily in a fairly straightforward fashion. So I produced this effect that was done by an account on Twitter called Science Porn. It looks like this. It's a bunch of circles. Well, you can see for yourself what it is. And it's just a quick little bit of Java code, and it came together quite nicely. A little bit of prototyping in there. And from here, basically I've also built a single header C file library for debugging. It does debug visualizations, and I thought, why not implement this as the sample code for that library? So I'm taking the code that's written here in Java. There's not much code. I'm going to convert it to C99, and I'm going to do it up in Visual Studio. Now, we're not going to do any window production or creation code or anything like that. The library will actually stream out to disk all the different lines and circles and points. So we can use a tool that I've created called SimpleVis, which plays back your debug visualizations. So I'll show you an example here. This is a bundled example of a platformer. So you see a bunch of physics objects. Once you press play, you can see it all simulate pretty nicely. You can get this in-game pretty easily. You can build a debug visualizer. One of the really nice things, though, is I pause this, is I can rewind your debug visualization. You can also zoom in. Now it's important you can step through the frames. It's important to note, still got some work to do on the panning, it's a little janky. It's important to note that it's not a video playback. What it lets you do is it plays back every frame. There are no dropped frames. What you're seeing here is exactly every tick in the game. So it doesn't play back in real time. It's more important that you don't drop frames. So you get things like this, where you see the interpenetration and separation. And if you're doing debug code, you need to know, did it interpenetrate and separate in one frame? Or was there a margin of error in there? A lot of times the debug lines and visualization tools are built into the engine. You don't have that ability. So this is a single C header file library. It's very easy to use. And we're going to build this graphical tool in here. We'll load it up in this tool called SimpleVis, and we'll see it all come together. All right, we can close down this. This is going to be the main file. I'm including some core routines and the SimpleVis library. All this code is going to be released in public domain, by the way. You can go ahead and follow along or do whatever you want to do with that. Okay. I'm just going to bring up, I have a second monitor. I'm just going to bring up as reference the code that... Whoa. Bring up the code for Pieballs. There we go. You won't see it on the screen. I'm also going to bring up the code. I don't use autocomplete. I use big monitors and separate documents. So this is how we're going to do this. I also have Visual Studio. I'll bring it up here. But I don't do most of my coding in there. I do my debugging in there. I do most of my coding in Emacs. Let's take a basic usage example. I'm going to follow my own documentation. Okay, so what we're going to need to do is a function called draw Pieballs, and it advances over time. So, where is it in here? It's frame count? Is how they do it? Frame count. Yeah. So processing uses frame count, which is just the number of frames. So I'm going to emulate that by going for int I equals 0, I equals 360, I plus plus, I void pi draw pieballs int frame count. All right, so we have the SimpleVis circle function, and the first thing we're going to do is draw the primary circle. So I'm going to say we have to set up a couple of constants here. Const 512 constant height equals width. Let's keep it a square for now. Bring up the chat as well, just in case anyone has anything to say. All right, I am watching the chat on the next screen. All right. So SimpleVis circle. Let's see here. Width divided by 2, height divided by 2. Radius is going to be almost the full 512 width times 0.95f. Color, we're just going to use a stock color for now. SimpleVis gray. I think I used the word gray with an A because I pretend I'm American when I name variables. I go back to being Canadian when I write my comments. And the line width for the circle. Ooh, that's right, the circles are not solid here. That's fine. Let's give it a 2. All right, so that's not very much, but it gives us enough to compile. Let's see what I did. Initializer is not a constant. Well, whatever. Conversion from float to int. Int to float. Frame count. FTG unused. Frame count. I'll shut it up for now. It's a little macro. All right. So this should create a pieballs.viz. And exit. Let's find that file. It did not. I have to... Oh, of course. That's not going to do it. I needed the shutdown anyways. But what I need to do is end the frame. I'll just do it over here. SimpleVis draw. That flushes the buffer to the disk. All right, bringing up the file. Copy path, clipboard. Bring up SimpleVis. Okay. What we have here is a circle, which is too large. And it's currently occupying one single frame. It doubles up. Why is it doubling up? I should be doing the exact same thing for every frame. Width divided by 2, height divided by 2. Let's go back to Emacs. Well, the frame buffer itself there is 1280 by 720, so if I just do that, I happen to know that the frame buffer in the preview program is 1280 by 720. The other thing is, it doesn't delete the file every time. extends it, which is great if you have multiple executions and you want to keep that around. And you can leap between them as well, which is nice. But I'm just going to manually delete the file in Explorer for now. I said manually delete the file in Explorer. Dropbox, plain text, quick, PS25. It's, come on, Pieballs. All right, I did nuke it. All right, let's rerun this. Let's refresh it. Did I close down the SimpleVis app? Okay. That's better. I see nothing. Awesome. It's too large. Screw it. File in use. Just going to run it. And hit refresh, jump to the next iteration. Okay, finally. The circle. It's totally my bad. Bringing up the chat. Cool. All right. We have circle. I draw the tracks now, so let's just call this like the, let's bring it in here. So come in handy when we do the tracks. Now we can have a number of tracks. Const float num tracks equals 8. And we can draw more. This is the lines that go through the circle for float on. I have a function for degrees to radians, and I want to use it. I just have to remember what. There it is. It's an FTG math. I should probably just include that. I have to implement it. So it's a single header file library. In this one, it's implement math. Nope. Primary rad should be float. I think that parameter is an integer, I thought. FTG, SimpleVis, circle. Oh, the radius is a float. Thanks, Brad. There we go. E equals degrees to radians. Yeah, my math library does not have any prefixes in the names. Consider it to be, if I have to type stuff like ftg underscore dot, it would just drive me crazy and make everything look messy. It's a little risk I'm taking. I actually prefer it that way though. E. So we want to draw a line, and the line starts and ends depending on the radius of the circle that we're drawing the lines in. So we can calculate that once. Float cx equals primary rad divided by 2f equals. I'm doing this twice because it can work for ellipses as well. Now, I also need to include, I think I implicitly include math.h if I include this. Yeah, okay, so I have access to like sinf and stuff. So back to this, when you draw a line goes from x1, y1 to x2, y2. So that's pretty straightforward. Cx plus cos f e times the radius, which should be the, oh, it's the radius is the circumference times 2, and that was why it was too large, is because I was trying to render the circumference in the first place. Okay, we can change a couple of things. For now, I'm just going to go primary rad. So that's the first x, cy times sin f e times primary rad. Cx minus cosine e times primary rad. Cy minus sin e times primary rad. Theory, that should get us the number of tracks we need. Conversion from double to float. Good lord, this is the sometimes. SimpleVis line xy. Duh. I need to pass a color. SimpleVis gray for now. Let's run it. Hooray! Obviously, I need to offset that. I need a centroid value. Let's go back to Emacs. Width, left, height. Let's call it center, let's not be pedantic. Cx primary rad, cy. Non-constant aggregate initializer. True. Did I close it again? I have to put a confirm in there. Okay, so I managed to screw that up. Let's see how. Pretty sure this is just an operations thing. Yep. Yeah, I'm an idiot. Look at that. And I don't know how to find the center of a circle, apparently. Let's take a step back. I need to calculate the circumference of the circle and then take the radius from there. Radius. That's what I should have been doing. Primary rad can die. Okay. And then center X, I'll just do it like this, equals width divided by 2. So equals height divided by 2. Let's cast that. Now when we draw the circle, we just go CX, CY. Let's do it again. And then we're doing by radius, not circumference. Would that piss anyone off? Does anyone care if they do circumference versus radius when defining a circle in a debug library? I've always thought radius was just the right way to go. I might be wrong. I kind of didn't really evaluate that when I wrote this. So I haven't shipped it yet. I want to put it to the test a little bit. All right. So we can't recalculate this. Don't need to. I got these primary rads in here. Let me just get this out for now. Can't not close it. Well, whatever. Here we go. Circumference? Something is not right. Ah, here we go. There we go. That's more like it. That is now, from here to here is now 95% of the way to the height of the thing, which is what we want. All right. Let's take another swing at these tracks. I'm just like rewriting the damn thing. I know this is what I want. Same as before. Honestly, I'm just going to replace primary rad and see what happens at this point. That's probably the best thing to do. With the variable radius, which is just their circumference times 2. Done. Let's build it. Okay, there we go. And we should be able to just bump up the number of tracks by changing this constant. So if I change it from 8 to 32, we'll see more tracks in there. Same thing though. Uh-oh. Oh, there we go. It's taking a little while to draw it, which is surprising. I'll have to look into that a little later. Speed of it make the difference? It does too, yeah, okay. Well, each one of these frames is being stored 360 times, but there shouldn't be much overhead regardless. Excuse me. Okay, so put that back to 8. Now we're on track. Get rid of this. The last thing to do to get the whole thing in there is to draw the motion points. It's the most involved and interesting part. Got to draw little balls that move up, back and forth. So just to bring it up again for reference. Those balls there are the motion points. And in enough, it should, well, I think it's 360 frames for them to go all the way around for a complete loop. Anyway, we're going to draw them so they interpolate on the tracks at the right speed, so they can go around in a circle. Just give me a sec here. I'm going to quickly delete the Pieballs file. We've actually generated 183 megs of data. This is not exactly a compressed codec. It's meant to stream to disk, that's for sure. Okay, 4 num track. So for each track, we want to draw the ball. I really need to fix that indentation. Emax equals degrees to radians. So here we take I times float 180.f divided by num tracks, and that gets us the position along the lines that we need. So basically there are 4 values, the minimum and maximum for each track in the line. We need to calculate the min and max, so basically the ends of the lines, not much different than what we did right here. And then we need to find the point along the line with the correct timing that makes it half a circle. So this is fairly straightforward. Float p min x equals cx plus sin f e times rad. Float p min y equals c y plus cos f e times rad. P min p max x. I cannot copy and paste code like this. This is where you make mistakes. I have to figure it out. Sin f times rad. Float p max y equals cy minus cos f e times rad. Okay, now we need to figure out where we are along that line. Just float frame count. Frame count, because it's animation, I'm just going to keep everything consistent here in terms of the naming. Frame count times things would blast by too fast, so I'm going to actually add in a slowdown coefficient. Float. This is a tune. This is what we call a tunable. Since the processing version already had it in there, I've got it to a point where as you've seen it. Let's get rid of that for now. So that's the point. We actually do not linearly interpolate the point to create the circle. We use a sine oscillation. One of the nicest things that I've totally taken out of processing is a function called map, which takes a value between an old range, min-max, and maps it to a new range and returns that value. So the function is right here, actually. You pass in the first parameter is the value, then you pass in the range, and you pass in the new range. It's kind of an assumption that it's already within the old range, and if you don't do that, then you're just going to get garbage data back most likely. But so this gets us the point. We can map between -1 and 1. We can map that to the new min and max range for each coordinate, and we'll have the position of the ellipse. So take the value, which is s, which is through the sine function, which gives us -1 to 1. And we map that between p min x, p max x, py equals map f. Same thing, I'm going to break my rule here and copy and paste. And then we draw the circle. Quickly check the comments. Modulate factor 101 over the animation with offset different for ball. Maybe modulate the rad. Modulate the radius. That'd be cool. I'm gonna do. I think there's definitely room for us to like improve on it and do different things with it. Show off some of the features once we get the basic in here. One of the fun things about doing these little animations is you're like, oh, hey, I've got this process that loops and it's got an animation to it. I'm like, how can I make a video game out of this, right? Like, how can you make this interactive? And there's like all kinds of cool stuff you can do there. This is sort of just the basis of it. You get a little bit of understanding of the math and you can take it in crazy directions, which I love. Okay, so we need to draw a circle here. Circle. And the radius is just the radius of the track circle, which I'll fill in that constant in a minute. And we're going really super boring for now, so we're going to start with S is gray, and we'll give it a width of 2. Oh, to calculate the position of the ball, maybe modulate the radius. Modulate with factor 1 over the animation. With offset different. Where's the video audio? Modulate with factor over the animation with offset different per ball. Sin FE equals R, and R ranges. Yeah, I see that. I see that relationship. Mantrial, hopefully the audio comes for you soon, since that's what we're talking about. -101 is cos f. Yeah, I can see that approach working as well. I'm actually referencing code that I wrote about a week ago when I did this in processing. SViz circle pxy. Just change the R purple. Oh, let me just X circle. Okay, I'm gonna build that out. Well, I changed the name of a variable and got burned. It's initialized but not referenced. That's because I don't use it anymore. What else you got for me? Motion from float. 2 for the width. Let's run this. Pieballs. SimpleVis. Oh yeah. Clear the screen, guys. It's really useful. Alright, we're going to run that again with a cleared screen. This is clear. Yes, that is exactly what I called it. I can read my mind. Let's delete that last file. I did not delete it. No worries. Explorer is acting up. I can still just run the damn thing. Alright, that's before. Let's jump to the next iteration. There we go. And there you have it. The basic animation is in. It's not going long enough. It's also not the prettiest thing in the world, admittedly. You got the non-filled circles. The point of this is a debug draw library in the first place, so you don't always. I'm not really aiming for the most pretty thing. With these lines, it's more important that you can see what's going on. So for example, if we want, we can easily just change that to red. Light red. We have a bunch of constants set, and there's nothing that stops you from making your own. It's just an array of floats. Slower than expected, no clear. No, I think it's slower because I'm writing to disk aggressively right now because I'm saving this video to my disk that I'm recording. And at the same time, I'm also streaming heavily from disk because this is a stream-based operation. I'm guessing that's what it is. But the clear should just be a matter of sending a clear to the device context. It doesn't redraw all the things every frame or anything like that. So I'm not sure why that overhead is there. Copy path. Okay. Just bear with me here. I'm going to delete the file. Plain. Quick. VS25 Windows. Hand delete. Oh yeah, of course it's open. It's the one time I forget to close the damn thing. Delete. Let's run it. It's only for going for a 360, which is the problem. It's not going far enough. So they're red now. Hooray. There we go. Let's do one fancy thing before we sign off. Let's give the pieballs a cool color. Right now it's red. I have a nice function here, which is the old RJ. So an SViz color, SimpleVis. An SViz color is a very simple structure. It's just a type def for float 4. So ball color. How's everyone doing? Ball. Let's see here. Let's modulate the color based on the frame count. Let's modulate the hue based on the frame count. So we just say frame count for the hue, frame count, saturation 1, value 1. Is that going to make it white? We'll find out quick enough. I think the answer is no. Let's set this to another color. C for color. If I've blown out the C yet, call is fine. I just don't want to type this a million times. Call 1. And SViz color is a float 4, so let's set call 3 to 1.0f. So, okay, so let's just pass that in here. And if I didn't screw up, we'll get something kind of neat. Run it, write to disk, refresh. Hooray! We now have animating colored shapes. So there you have it. That was the creation of the Pieballs animation using the SimpleVis library. It is a single C header file, and the compile time is ridiculously fast because you don't have to link pretty much anything. You're just writing a file to disk, and the visualization is in a separate address space. So thanks for watching. Thanks for sticking with me for my first ever stream, and I'll see you soon.